All right. Okay, let's get started. So the redo of lesson 1 of the control or short course in control theory. Okay, so let's start. So during this short course, so as at the time of the recording, this is actually a redo of lesson 1, but in general we try to teach you guys both continuous domain control approaches, and then we try to get over into discrete domain and show how to do similar approaches. So first and foremost, in general, all control systems are multivariable cross-coupled states. They have multiple inputs, manipulated inputs, and manipulated input can be cross-coupled. So there's a lot of different issues that we might find. So we have multiple variables. We have cross-coupled states. And we have multiple inputs. We can have multiple manipulated inputs. And they can be cross-coupled as well. So multiple inputs are usually short like this, and we have manipulated input cross-coupling as well. Can be cross-coupled. Okay? So we try to teach you how to handle all of these issues and many different other things as well. So, and then we have to look at what do we actually try to achieve with our control. And many would argue it's a lot about command tracking, that we have a command and we try to track that command, and that's ultimately what our controller tries to do. However, when we talk about state feedback controllers, I would argue that disturbances are the most significant issues. And we'll see during this course why that is. But I would state that disturbances are the most significant issue. And to evaluate a control, we have to talk about mainly 3 matrices to basically tell how good our control is, or at least that's what we propose, is first of all disturbance rejection. Second would be command tracking. And the third would be robustness. So to just clarify what all these words mean, disturbance rejection is probably very intuitive, right? It basically means how well can we reject something that we don't want, like a disturbance. The second command tracking also very straightforward. We know we have a command, we have a reference that we want to track, and how well do we actually track it. And both of these have to have like a dynamic matrix that we will have to look at, and we get to this very soon. And the third is robustness. And what does robustness mean? What's the word robustness implying? Do you know?
Is it reliable?
You would think it means reliability, but it actually means, so in control terminology, this means parameter sensitivity. So in control terms, when we talk about robustness, we always mean parameter sensitivity.
Is meant less sensitivity or?
Yeah, if you're robust, if your control is robust, you're not very sensitive to your parameter estimation.
This parameter is
Every parameter of your system, for instance, for your current control, your Rs, your Ls, how well do you need to know them in order for your system to work? So if you know that your system still behaves very well with even 30% parameter estimation error, then that's what you basically can tell. If that's robust enough, that the application tells, right? But that's basically what you need to find out. When you talk about disturbance rejection and command tracking, you always have to have in mind that you never know your parameters correct. You know them in a certain range.
Yeah.
And is that still okay? So whenever we do these, always have in mind that we have parameter estimation accuracy, just to a certain point. So that's when we talk about robustness, we always talk about how sensitive are we regarding parameter estimation. Okay, so that's the big points that we want to basically teach you, and in all the both in continuous domain and in discrete domain. And to get there, we first of all have to converge us on the same basic concepts of controls. And that would be drawing our block diagrams. The control that we teach here, we call it physics-based control. Or physics-based modeling, what we do now. Yep. I don't know who gets the credits for this, but I learned this at WEMPEC with Professor Lorenz. Yes. Okay, so we start with our first example. Example 1. It would be the suspended chair. This doesn't come very nice. So I'll use a different color for now. So use a chair example. Could be really anything, but we have a mass. We have a spring, which has its stiffness coefficient of K, and we have a damper. Okay? And we have an actuating force here. We have a disturbance here, for instance gravity, which we can very easily decouple because we know exactly what it does. And we have a position this way. And now we try to start with the modeling. So first of all, always a differential equation, right? That's the first thing that we start with. And here we can use Newton's law that the sum of the forces will equal to M times A, correct? Which means that this is M dxt squared, correct? Okay. And this also equals, so the forces are basically the actuating force, and I also so then we also have the forces because of these components, right? So we have the spring force, which depends on the position, and then we have damping, or in translation motion, that would be like a friction term, Cp times the speed. And then we also have our disturbance, right? And we keep it, well, this, so the state format of this, or the state space format would be to put this in the terms of the derivative. So we would basically first of all say that dx dt is our v of t, and then we could put this into the format of the derivative of the state. That would be the state space format, basically. What we suggest, though, is that we use the state block diagram format. And the main rules here for this is that we keep everything in the units of the manipulated input. What would be our manipulated input? It would be this actuating force, right? If we try to actually have influence on the system, this would be our manipulated input. So we keep it in this format. And you'll soon see why. Because it actually makes it so that all our gains in our state block diagram will still be physical. And that's also why we call this physics-based modeling. Because everything makes a lot of physical sense. That helps to both understand the system and to design it very nicely. So we keep it in this format. So everything is in the unit of force, right? So it's basically friction force. This is the friction force, this is the spring force, this is the disturbance force, the actuating force, and this is basically the force that acts on the mass and does an acceleration. So if we keep it in the state block diagram format, this will now actually and we always start from the left with our manipulated input. Up here is the disturbance. So the disturbance is gone. We also have, here we keep for the, so we try to get to dv dt, right? So we have to basically get rid of all of these. So there will be minus, also Cp and v of t going in here. There will also be x of t going back, right? Which means this here will be m dv of t dt. Which also means 1 over m. We get v dot of t, and with an integration, we get v of t. So we can close this here. And another integration yields us x of t. Oops. And we can close it like this. Right? And this is our now physical or physics-based state block diagram, which helps us really to see what's going on. And all these parameters are now that are in here are very physical. This is the mass, this is the friction component. So these are all forces, the friction forces here, the spring forces here. And these make a lot of sense if you write them like this. Now we talk a little bit about terminology. This here is the state having a gain and feeds back. So that's why we call it a physical state feedback. Oops, feedback. Or SFB is our short pronoun for this. Both of them are physical state feedbacks. And in our system that we can control, we'll have something built that gives us basically access at this force, right? We have a force modulator, something just to make sure that we can set this force. And this should be roughly a 1, so I put here roughly 1, which means we have, in our controls, we have access at this point, right? And we can play around with this mathematically. So if we wanted to, instance, increase the damping of the system, we could also measure the speed, give it a gain, and subtract it here as so. So what does this physically do? As these 2 points are basically the same, and I do the same thing as this, right? It technically only makes this feedback bigger. And we call this an active state feedback. Because we create this. This is not a physical, it doesn't happen because of physical things. And there's also not energies involved really, because this is just math. So this dissipates energy, this doesn't. But we still get damping attributes or damping attributes on it. Okay, that's the nice thing about active state feedback. We get the properties of the physical state feedback, but we don't have the same, or not like energy is dissipated. Okay. So now we want to talk about transfer functions and attributes of this that we can dynamically basically tell what our system is doing. And to dynamically, or to know dynamic performance, we usually go into the Laplacian domain. Really helps us, right? These are integrators, and we can use just these integrators if our system is linear. If it's non-linear, Fourier transformation or Laplace transformation doesn't work, right? So in this case, it's a linear system, we could have done this, so we could replace just the integrator with 1 over s. And that's very nice because now it's very easy to get a transfer function. And the first transfer function that I really want to look at is what we call dynamic stiffness. Dynamic stiffness is the metric of is basically the inverse of the transfer function seen from the disturbance to our state. Okay, so and it's the inverse basically, or it's basically the state in this case, Es over Fd of s, the inverse of it. So this matrix basically tells us how many units of disturbance do I need to change 1 unit of our state. Or in other words, it tells us how stiff is our system in regards to our disturbance. So if this value is really, really big, that means you need a lot of force to actually, that's the inverse, right? You need a lot of force. This helps to see this. So this value is very big, you need a lot of force to change 1 unit in the state, right? So big dynamic stiffness tells us we're really stiff in regards to that disturbance. So let's try to do the math for this and see if we can make physical sense out of this. So for this we will use, and now without this active state feedback, we use basically Mason's gain rule, and I'll do first this and do the inverse of it. So I'll start with the transfer function, so it's the open loop, closed loop, and this again, closed loop over it. And I'll rush through the algebra real quick so that we can actually talk about what's going on. wind up with this formula. Okay, that's our dynamic stiffness. And if we plot this now so as a frequency plot, and we want to basically plot the magnitude, so what we try to do is do the magnitude of FD of S or V of S. And do it in a logarithmic or double logarithmic plot. The exact values of those here doesn't matter, it's rather just to show that it's a double logarithmic plot. So down here's frequency, up here's the magnitude. We maybe first have to talk about what is S, right? So S, what is S?
J omega.
S is J omega, right? So in most cases there's some restriction on this, but mostly it's J omega. So if we look at the magnitude, it's omega, right? Or 2 pi f. So that means if we can plot this now, even without doing any math or knowing any parameters, we basically know what will happen at low, mid, and high frequencies, right? So let's start at small frequencies. If our frequency is really small, we can show what dominates up here. What dominates here?
Frequency very small.
Yeah.
Ks and Cp.
Yeah, but let's say S is almost 0, then this here definitely by far is the biggest, right?
Yeah.
So by far, this whole system becomes Ks over 2 pi f. Which means it goes down by 1 f in a double logarithmic plot that's 10 decades per decade down. So we should see something like this here. So 1 decade per decade might not be perfect, but 1 decade per decade is so negative. Okay, so the frequency increases. At some point, something else will start to dominate, right? So the medium at medium frequency, at some point, this here will start to dominate, correct? Depends on what the actual values is, but this will get lower and lower and lower, right? And Cp over the whole is just a straight line, right? It doesn't depend on frequency. So if Cp is something like this, the whole curvature at this point will be this. And at very high frequencies, obviously, something else will dominate, and that is our m times s. So m times 2 pi f. Because that's always going up, but at 0 at 0 goes up here somewhere, and then it will start to dominate. So that's basically naturally how this system would look like from the disturbance. And now let's see if we can make physical sense out of this. So first of all, so this is Cp, and this is m times 2 times f. So first of all, let's talk about some terms here. We see two things happening here. What do we call these points?
Corner frequency.
What do you call it?
Corner frequency.
Corner frequency, yeah. There's that too, or cutoff frequency, break frequency. The system breaks, so a lot of people call this a break frequency. So there's many words for this. This is also actually the eigenvalue of the system. This will be the eigenvalue, the break frequency, cutoff frequency, all these different terms, but all of these are here. They all basically mean the same thing here. Okay, so we have these here, and we will see that it's really easy to calculate them. But first of all, let's see if this makes a lot of sense to us. So, in this area here, the higher the frequency, the stiffer the system becomes because of the mass. Does that make sense? Like, come up with an example where for instance, the friction is almost zero, the stiffness is almost zero, and you only have this. Maybe I said just like a ship in the water. The ship is super, super heavy. But at very low frequencies, let's say DC, can you move a ship although it's super heavy? Yeah, have you tried it? You've seen these large ships and you can actually push them, right? Have you ever tried to push a boat?
Boat, yes, but a big ship, no.
I mean, by very, very little, but let's say a boat, right? You can actually push it. If it was on the ground, you couldn't, right?
Yeah.
Impossible.
No.
You cannot push it on ground. Why is that? Because on ground, this CP value is really big. In water, it's way, way lower. That means actually only this is there. I mean, almost. This is also there, but only really this is there. So you can push the boat very slowly, and you can actually accelerate as well. But could you move it back and forth easily?
Yes.
Like quickly? Imagine a boat, you can push it, but can you push it back and forth quickly?
No.
No, you cannot. Because you use a high frequency. Mass is an energy state for this. It's an energy state for speed. So you cannot change speed fast in a boat. But you can actually accelerate it. You can slowly, you can use a very low frequency. So at low frequencies, mass is not a problem. Mass does not have high dynamic stiffness at low frequencies, but at high frequencies. And you can feel this. You cannot move a ship back and forth, but you can move it in one direction. Okay? So this makes a lot of sense to us that mass looks like this. So let's use the next, maybe here for the CP, for the damping or friction coefficient. It's, for instance, something that has very low weight and no stiffness associated, like maybe the pen on the table, right? Do you feel a difference of force that you need if you do this like really quickly or if you do it slowly? It doesn't feel like it's getting harder to do this. Maybe by a very, very little, but that would be just the force. But really it feels almost the same. But you need a force. The direction changing the static friction you might feel a little bit, but it doesn't really depend, it only depends on how fast you are, but not on the derivative. It's maybe hard to imagine, but that's what really friction does. And then think about something that has stiffness associated, or that has a spring associated with it. Let's assume, do you know these rubber bands that people use to train in the gym?
Yeah.
Let's try to put it to a wall and use the extreme case of DC. What would DC be for speed? That means like a constant speed, right? Could you use a constant speed on a rubber band? Could you just keep going? No problem. No, you couldn't, right? Because the force is getting bigger and bigger and bigger. So it's infinite force that you actually need for a constant speed. Right? This goes up and up and up. At constant speed you need infinite force because the force is getting bigger and bigger with the spring. Right? So it makes a lot of sense that at DC you have almost infinite stiffness because of a spring. If it doesn't break, that is, right? It's not physical, but it really goes up a lot. And at really high frequency, let's assume it's not even starting to have force yet, and you change it really fast, but the x doesn't really change because your speed is changing so quickly, you never even feel the force because you haven't even contracted it yet. Right? So at really high frequencies, there's no stiffness because of a spring. So really these three together shape how you behave to a disturbance. Okay? So I hope this makes a little bit of physical sense, like how these interact and how they look like from a disturbance. The same is for your current control. This basically looks like your resistance, this looks like an integration, for instance the I of your control, and this is your L. So you shape basically the impedance that your grid sees. And you should shape it wisely, because if you don't shape it wisely, it might do something weird, or it might be oscillating, or something like this. So always rather think about this when you create your state feedback controller, than thinking about the command tracking. Because we will see, command tracking usually is not that big of an issue. You usually use feedforward to do this. Anyway, so, but now let's also come to how do we know where these break frequencies occur. So where does the break frequency 1 occur? What happens at this point? At this point, this stops dominating and this starts to dominate, right? So exactly at this point, what is the relationship between the two of them? Or here, sorry. They're the same, right? It's exactly when this line meets this line. So at break frequency 1, ms equals Cp. Correct? And we said S is basically 2 pi f for the magnitude. Then we knew that 2 pi f break 1 times m equals Cp. So if we know m and Cp, we know where this happens. Or if we want to have it at a certain frequency, we can also choose these parameters accordingly. And for the second break frequency, same idea, right? This is when these two are equal. When these lines meet one another. So that's where the second break frequency happens. And so that is when k over 2 pi f break 2 equals Cp. Okay? So this way you can either calculate the break frequency, or you can basically calculate the parameters, whatever you want. But if we make physical sense out of this and have this metric, it really helps us to both understand what's going on for different frequencies, and we also really easily derive where all of this is going to happen. Is this clear so far, or any questions on this?
Yeah, sure.
Okay. All right. Let's go to example 2. You will see the differential equation looks pretty similar. We have a mass ground associated with some friction coefficient. We have our actuating force, we have a disturbance force. And we go into this direction. So the formula very, very simple again. Fa of t minus Fd of t equals, or minus the friction, minus v of t times b equals mdv dt. Right? So we can basically draw a state log diagram again. Let's do it for this case. Looks pretty similar. Because if we look at this, here it is in the B here. Oops. Okay. So we have our active state feedback here, right? And if I redraw this a little bit, I don't change the system really. So I put a minus here, make this a plus, so it's still the same. And I add a 0 here. Doesn't do anything, right? It's the same thing as before. This minus
Yeah.
should be the same as before, right? We call this a virtual zero reference. How does this look like to you? You have a state, you have a reference that's 0, and you have a gain, and it goes into your manipulative input and changes something. It looks like a P control, right?
Yeah.
So the state feedback basically looks like a gain for a reference that is 0. So it draws back your system by itself, which is common in almost every physical system. Here's it's our friction, so if you start a mass moving, it will by default go back to 0, right? And that's the state feedback that does it, because it gets a reference at 0.
Yes.
So it tries to draw back your system to 0. And I guess this is a problem, right? So